Okay, thank you very much to the organizing for letting me speak here, for such a wonderful audience. So let me start by mentioning that this is all based on joint work with Karim and Ibrasito. And let me give you an outline of the talk. So what I'm first going to do is I'm going to introduce the main problem that I want to talk about, which is a conjecture of Kalai. And it relates the combinatorial structure of polytopes to certain approximations of convex bodies with sufficiently smooth boundary with polytopes. Then we're going to I'm going to try to give a sketch of the proof, emphasizing why the smoothness comes into play, which is the reason why I actually got interested first here. Why is smoothness playing a role in the study of convex polytopes? And then I'll state an open question by Kalai, which is the analog, and I'll explain basically what it would mean to approximate convex body with a polytope. So I'll start saying that all polytopes that I'm going to consider are simplicial. And as Eran was talking earlier, I'm going to be considering the F vectors of polytopes. So Fi here is just the number of faces of dimension I. And in a similar way as Eran did, I'm going to consider the H vector, which is just the transformation of the F vector. So we change this polynomial, we get the H vector. And the reason why this H vector is nice, as Eran already explained, is because we have this symmetry. For example, the Euler characteristic of a polytope is given when we take I equals to 0, and we have also this unimodality that allows us to define the G vector. So the G vector is given by G0 equals to H0, and the GI is given by the consecutive difference, so HI minus 1. And again, as mentioned by Eran, for simplicial polytopes, the G theorem completely characterizes these G vectors as simplicial polytopes. And what I'm going to talk about right now is about how so this can be thought of as, if you give me a G an integer sequence, there's a numerical process to determine whether this sequence comes from as the G vector of a polytope. And what I want to do is show that for polytopes that approximate a smooth convex body, these inequalities are far from being tight. So let me also recall a nice result which was just mentioned by Eran, which is the result from last year by him and Satoshi, which says that if a polytope has GI equal to 0, that's equivalent to having a very nice triangulation. And this triangulation of the polytope, what it's doing is not introducing faces of small dimension, right? So this means that we have a triangulation sigma of p in such a way that all the faces of dimension at most d minus I are the same in triangulation in the polytope. So I think Eran just explained this a few minutes ago. But let me go on and try to explain what it means for me to approximate a smooth convex body with another one. For this we need a notion of metric, and the metric that we're going to use is the Hausdorff distance. What's the Hausdorff distance between two sets? It's just look at all the points that are in A, compute the distance to B, then look at all the points that are in B, compute the distance to A, and then take the maximum of such a thing. That gives us a distance, a well-behaved metric on the space of bounded subsets of Rd. And I'm going to say that a C1 convex body is just a compact convex subset of Rd that has non-empty interior faces and has boundary of type C1. That means that the boundary is locally a function of a is locally a C1 function. And if you don't want to think about C1 or anything like that, just think of the ball of radius 1, and that's actually a very good example. So the question is, if I'm approximating a smooth convex body with polytopes, are there any obstructions to the F vector theory or the combinatorial structure of the polytope that arise from being close to a convex body? So here's a conjecture of Kalai in 1993 that says that if you have a sequence of polytopes, so if you want to construct a sequence that converges to a smooth C1 convex body M, then these G numbers are going to infinity. What does that mean? They're far away. So we know from the Murai-Nebo characterization of Gi equals to 0 that we can classify the polytopes with Gi equal to 0. We're far away from that. Okay. So what I want to do now is announce that this conjecture is true, and what I want to do is give an idea of why this conjecture is true whenever 2I is less than D. Okay, so here I'm going to try to explain why smoothness is playing a role. Okay, so how does the proof go? We're going to go by contradiction. We're going to assume that the sequence converges to M, but the GI is bounded by some G. Okay, and the main strategy is going to be, we're going to find a simplex, all of whose edges are edges of the polytope, but it contains a point in the interior of the body that is far away from the boundary of the body. Okay. So as I was already mentioning, the main ingredients that we're going to use to actually construct such a simplex are the generalized lower bound theorem by Satoshi and Iran, and we're going to study the F vector theory locally for links of vertices. So what do I mean by studying the F vectors locally? For a polytope, I'm going to define the link of a vertex to be the set of all faces of the polytope, so that if I take F, V, and take the new convex hull, I get a face. And this is equivalent. It's going to be important. This is the same as a simplicial complex. If I have my polytope and I have a vertex here, this is the same as cutting the polytope with a hyperplane that is very close to the vertex, and we get another polytope. Okay? So we can think of this link as a polytopal simplicial complex. And then it can be shown that, following a trick from Ed Schwartz, that if we go and sum up all these GIs for the links of the vertices, then we get a combination of GI plus 1 and GI. And the very nice thing about this is, so the G theorem gives us an M sequence, so it tells us that G numbers form an M sequence. And if you think about it, that gives us a lower bound. This gives us a bound for GI plus 1 in terms of GI. So this sum of all these links here is bounded by some function of GI of the polytope. Okay? So why is this nice? As I mentioned, all these links are polytopes again. So these summands here are non-negative. And that means that almost all of them, so if we're going to infinity, it's easy to see that the number of vertices goes to infinity. So almost all the summands in this sum here have to be 0. Okay? So from now on, I'm going to refer to as the good vertices. So I'm going to refer, the good vertices are going to be the ones such that this GI is equal to 0, in which we're in an ideal situation to apply the Murai-Nebo result, and the other vertices are going to be called bad. Okay? So what are we going to do? I want to construct a simplex using the trick of Murai-Nebo. So what I want to do is exclude all the bad vertices in some way. So to do that, we use a hyperplane separation theorem that says that if we take any set of any finite set of points inside the smooth convex body, then there's a hyperplane that separates those points from the boundary in the following sense. All the bad points are in the positive part of the hyperplane, and then this hyperplane intersects the interior and has a point that is far away from the boundary, at least some epsilon that only depends on the number of vertices. So what can we do with this? Let's construct Hn, the hyperplane given by this lemma, if we take the bad vertices, all the vertices whose gi is positive. Then we have that all the vertices in the negative side of the hyperplane have gi of the link equal to 0, so we can actually take a triangulation for this thing. Then we can cone this triangulation. Oh, I didn't write it, but we can cone this triangulation. We get a lot of simplices whose one skeleton, or whose d minus 1 minus ith skeleton, but in particular all the edges are contained in the edge of the polytope. And we can take the union of all these simplices. Okay, so I have a collection, a huge collection of simplices, such that the edge of each of these simplices, all the edges of these simplices are contained in the edge of the polytope. And then the very next thing that happens is that if we take the union of all such simplices, we call it sigma n, then when we intersect sigma n with hn, we get the exact same thing as if we intersect pn with hn. Okay, so to illustrate it, here we have our polytope. The blue points here are the bad vertices. The green points here are the good vertices. Notice that in the negative side of the hyperplane we only have green vertices. And if we construct this triangle, so let's say that these triangles that I draw here are the cones over the Muraino triangulations. So what we get is that the intersection of this sigma n here with the polytope is the exact same thing as the intersection of the union of all these simplices. Okay? So why is this nice? Because either there's a point, so either the intersection is empty and then the polytope is far away, or if the polytope is close enough, then the point in this hyperplane that is far away from the boundary is contained in one of these simplices. So what's going on there? So what we managed to find is a point that is at least epsilon apart from the boundary, that is contained in a simplex, all of whose edges are edges of the polytope. But here's where smoothness comes into play, because what happens? We could actually try to we could construct a topological space that parameterizes all these simplices that contain a point far away from the boundary. And the distance from the edges to the boundary of the convex body is a continuous function in this space. This space can be shown to be compact. If we look at this function, then we get a minimum. And if this minimum was to be 0, that means that that would mean that all the edges of this polytope lie inside lie in the boundary of the smooth convex body, or the C1 convex body, but that actually contradicts smoothness, because we can take partial derivatives in the direction of the edges, and that gives us one direction too much for having a tangent space. So why is this a contradiction? We found what we found is an edge of the polytope that is far away from the boundary, but then all the edges are squeezed. So if we think about moving the polytope to contain the origin in the interior, then as we squeeze, so if we contract the body a little bit, we can show that as n goes to infinity, then the boundary of the polytope is squeezed between the two copies of the convex body, and that means that the edges are all very close to the boundary. So that's actually how the proof goes. And now let me quickly, how much time do I have? 10 minutes? So let me briefly mention that actually for the case when 2k is equal to d, we can do something similar. We can use a brand new machinery by Fernando Di Prosito and Raman Sanyal, called relative standardized theory, to actually actually do the following. So if we take a polytope that is squeezed between 1 minus epsilon m and m, and we assume that gk is bounded by g, then there exists a hyperplane that does the following. So first of all, as in the separation theorem, it's far away from the boundary. So it contains a point in the interior of M that is far away from the boundary. There's a simplicial complex, all of whose vertices are vertices of P, and such that P intersection with the negative part of the hyperplane is equal to the intersection of the simplicial complex with the negative part of the hyperplane. And also, if we look at the skeleton of the simplicial complex intersection with this negative part of the hyperplane, we get the same as the intersection of P with the negative part of the hyperplane. So doing this, we can repeat the previous argument with the nice triangulation, and we actually get the result for the remaining case, which I didn't mention it before, but in this case, if 2k is equal to d, these gi's so this polytope is one dimension less, so this gi is 0, and this technique breaks down. So that's one of the things that's also done. But let me finish by saying by completing the explanation of what Calais' conjecture originally was. So this part that I just explained is the lower bound theorem, the lower bound part of Calais' conjecture, which gives us a lower bound in the number of faces that approximate the convex body. But also there's an equivalent. There's another upper bound theorem. So the G theorem says that this operation here, I'm going to define what this delta k is in a second, with this partial case in a second, but the upper bound theorem tells us that this thing here is at least 0. So for example, for cyclic polytopes, we actually get equality here. But this other part of the conjecture is also telling us that polytopes that approximate a smooth convex body are also far away from being tight in the sense of the G theorem upper bounds. Okay? So what this operation means is just that we can write, so if we take a pair of integers n and k, then we can write A as a sum of binomial coefficients that depends on k, and then this operation is just a shifting of the coefficients. And then that's pretty much the other part of Calais' conjecture. And if you think about it, if you think naively of the G vectors of polytopes as some sort of cone, not exactly that, but some sort of space of points, then what Calais' conjecture is saying is that polytopes that are approximating a smooth convex body are in the interior of this region of vertices of G vectors. Okay, that's everything I had to say, so thank you very much for
Any questions?
So what if the convex body is not smooth but has finite many singular points? And so then I ask, for example, if the G vector is bounded, what is the maximum number of singular points on the boundary?
I think that all you really need is just having a point, having an open set of the boundary that is of type C1 and is positively curved. So you just don't want to have flat, but I think you can have lots of singularities.
Okay, my conjecture it can be very few, like 4.
It could be even less, because in the argument, when you're actually constructing the simplex, you might have to slice the convex body with a hyperplane, and you can be in the 2-dimensional case. But actually, the separation theorem, so you can actually do the separation theorem and avoid the singularities.
Yeah.
So you get something very simple. If you have this region that is curved nicely. So you could, I mean, you want to have the curvature thing, because otherwise we take polytope, that's going to fail.
In Calais-Applebaum conjecture, so is it possible that maybe all of the phase numbers, all of the G numbers are more or less the same up to constants? So can you go back to the last conjecture? Yeah, so in Calais' conjecture is about the rate that the G numbers increase
Yes,
about
it's
they cannot,
controlled.
yeah, and but maybe you can just say that the GK plus 1 is not more than a constant time.
No, that's false. If you do the connected sum of the polytope with a cyclic polytope with lots and lots of vertices, you can actually still make it be very close to the complex body, but that makes the GK, so the increase to be almost optimal. So you actually really need the difference.
So is there a way to make this lower bound theorem more concrete? So not like as a limit, but so we're saying I have like n vertices and it's like this close to a convex body, then it has to have this many edges.
Yes. So for a sphere, you can actually, I once computed explicit bounds. We can talk about it afterwards if you want. But you can actually compute more or less explicit lower bounds for the sphere, and for general convex bodies of type C2, there are some similar tricks that you can do, but they depend. So it's actually complicated. You have to compute complicated integrals to produce the explicit lower bounds, but that can be actually done. So I can tell you more or less what the rate of convergence is. Like, so you have something optimal approximation with a fixed number of vertices. What's the distance?